So welcome to the materials revision video. For this, you're going to need roughly about 2 hours of free time, probably. The run time is about 50 minutes, but you're going to want to pause it to write things down, to think about things, and maybe rewatch bits of it. You're essentially going to be producing a mind map on all of the materials. So to do that, you're going to need a sheet of A3 paper to write your mind map on, or A4 if you think you can write really, really small. I'm going to be using 4 colours of pen, so black, blue, red, and green. And if you've got those, then you'll be able to duplicate what I'm doing. You'll probably also want your materials booklet to look up what we did in lessons, possibly a copy of the formula sheet and your textbook or revision guide so you can look things up as we go through. So when you're ready, move on to the next slide and get started. So the first bit of the materials topic was density. So try and remember what density means. You can think of some examples. So, for example, what would it mean if you were on a tube train and you said that the train was very densely packed? Well, you mean that the people were really, really close together. So, density is a measure of how closely packed the particles are in a material or substance. So we could draw some diagrams. And then we could draw another one like this. So this is more dense because the particles are close together, and this one is less dense. But that's not very specific, so we need to be a little bit more specific than that. And we say it's how much stuff there is in a certain amount of space, except we don't use the word stuff in space. We say it's the amount of mass. Amount of mass, we use the word mass instead of stuff. And instead of space, we're going to say in a certain volume. So how do we write that down? Well, we say that's the mass divided by the volume, which would give us the density. Mass, let's put a red box around that. So mass is measured in kilograms. Volume is measured in meters cubed. And this is density. Now we've done kilograms divided by meters cubed, so the unit is kilograms per meter cubed, written as kg meters to the minus 3. So the amount of kilograms of mass in a meter cubed. This funny symbol is not a P, it's the Greek letter rho, which looks like that. So mass is easy, measuring mass is easy. You can use a mass balance. Measuring the volume is a little bit harder. So you might need some formulae for this, which come off the formula sheet for the most part. So if you've got something like, say, a rectangular or cuboid object, then if you multiply length by width by height, you get the volume. You might have a cylinder, like so, in which case you'll need to find the cross-sectional area, which is pi r squared, and multiply it by the height to get the volume. Or you might have a sphere, and the volume of a sphere is 4/3 pi r cubed. Another way of working out the volume is by using something called a Eureka can. And you fill it up with water. So some will flow out of the little side bit. Once it's reached a level just below and there's no water flowing out, then you can put in your object. So if we have an object in there, the water will flow up and out, and into a measuring cylinder, like so, and then you can read off the volume from your measuring cylinder, and the volume of the water displaced will be the same as the volume of the object you put in. So that's a Eureka can. And the last thing I'll mention, which isn't particularly on the specification, but it's useful to know, is let's just talk about floating and what role density plays in floating. So imagine that you had a boat. Here we go, this is my amazing boat. Now the boat has a weight pulling it down, and there must be an equal and opposite upthrust. Oops. Let's try that again. Mass of boat times g. There must be an equal and opposite upthrust pushing it up. Now let's imagine instead of a boat, we created the same little hollow of water, but this time filled it with some water. The upthrust is the same. So therefore, the weight of that water, weight of water, weight of boat. So the weight of the water displaced must be equal to the weight of the boat. Because the little forces of upthrust on the water, whether or not it's a boat there or whether or not it's a lump of water there, the upwards force due to that water will be the same in both situations. So, weight of boat equals weight of water displaced. So to float, the object must be less dense than water. In other words, same weight or mass takes up more volume. If it took up less volume, then the water would kind of rush in over the top and it would sink. If it takes up more volume, there must be a little bit of that volume sticking above the water, and that's why it floats. So that's density. So the second bit of this module is on Hooke's law. Let's rule off after the last bit. So you will have looked at this initially by considering some springs. So if we imagine a spring with an original length L, and then we add on a bit of mass, the spring stretches slightly with some extension which I'm going to call X. You might call it delta L. So there's our extension. I could then add on another bit of mass, and I expect the spring to stretch a bit more. But the extension is always measured from the original length that it started with. The weight or force that you use to extend the spring is equal to the mass that you add on it multiplied by the acceleration due to gravity. And what you'd notice is that every time you added a mass on, the extension increased by the same amount if you add the same mass. And in fact, if you double the mass or weight that you add onto it, if you double the mass or force stretching the spring, you will double the extension. Now, we say that materials that behave like that are proportional. So Hooke's law states that the force extending a spring is proportional to the extension. Proportional means they increase in proportion. If you double one, you double the other. Force proportional extension up to, and we'll look at that in a second. The way we'd write that, we say force is proportional to extension, but we'd replace the proportional sign with an equal sign and put in a constant. Like so. X is the extension. Measured maybe in meters, although it could be in centimeters. The force F is measured in newtons. And this is the constant that links the force to the extension. It's different for different springs. Some of them might be harder to stretch and need more force. So we call this the spring constant. It's a constant that's linked to the spring. Now, if we rearrange that equation for K, we can see that K is going to have units of force divided by extension, which is going to be newtons per meter, or newton meters to the -1. In other words, I'm going to need to leave a little bit of space so I can fill that in afterwards. This tells us, it's measured in newtons per meter, it tells us how many newtons of force are needed to stretch the spring by a meter. A spring constant of, say, 20 newtons per meter would mean that you'd need 20 newtons, or 20 of those 100-gram masses, to stretch your spring by a meter. Now, if we plotted that on a graph of force versus extension, every time you add on a bit of force, you get a certain amount of extension. Add on a bit more force, you get the same amount of extension again. And so you'd end up with a straight line like that. Eventually, you would reach some point that we're going to call P, which is the point at which the spring becomes permanently deformed and it stops being proportional. And this is called the limit of proportionality. And that enables us to finish off our definition for Hooke's law. The force extending the spring is proportional to the extension up to, and there'll always be two marks for this question, one for the first bit and one for this bit, which is up to the limit of proportionality. And that should go in a red box because that's quite important. Now, supposing we had a stiffer spring, to get the same extension here, if it was stiffer, it would need more force. So we'd expect the line to be higher up. Let's put stiffer. But to get the same extension for one that's less stiff, we'd expect to have a smaller force to get the same extension. So that's less stiff there. Now the gradient of this line represents what? Gradient is change in what's on the y-axis divided by the change in what's on the x-axis, which is force is on the y-axis and the extension is on the x-axis, and force divided by extension is the spring constant. So the gradient is equal to the spring constant. So stiffer springs have a steeper gradient and so they have a larger spring constant. Which is why the spring constant is sometimes called the stiffness. So let's put this in green, the spring constant or stiffness of the spring. So let's imagine that instead of just having our one spring, we actually put two springs, one after the other, in a series. So we've got extension from the first spring and an extension from the second spring, extension 1, extension 2. So total extension is twice the extension for 1. With the same force. So as K is F over X, if we get twice the extension, X doubles, extension doubles, then K will halve. K in series, so for two springs in series, the stiffness or the spring constant is half. They're going to be less stiff because you get twice the extension for the same force. However, in parallel, like so, let's just change colour to blue. Oh, that's going to be a rule off after that bit there, which tells us what the spring constant is. So here, the total extension is half, because you have to stretch both springs. Or, another way of thinking about it, you need twice the force for the same extension. So as K is F over X, if the extension is the same but we need twice the force, F doubles. So K doubles. So K parallel is twice as doubles. So that's all there is on Hooke's law. Let's move on and have a look at energy stored. Okay, so on to part 3, which is on energy stored when you stretch a spring. To work this out, we need to use the equation for work done. So work done is force times distance. Remember that if you do work in stretching something, that energy is stored in the spring. So work done is force times distance, the same as energy stored. So let's have a look at, again, our force extension graph. So that's force and extension. Now, to get the first bit of extension here, and to get the second bit of extension here, requires different amounts of force, which poses a problem. Force isn't constant when you stretch a spring. So instead, we're going to use the average force. Now, because this is a straight line here, Let's call the maximum force F. So the average is going to be half of the maximum. Max force divided by 2. So in our work done equation, which is equal to energy stored, the energy stored is going to be a half of the maximum force F multiplied by the maximum extension. And that's where the factor of a half comes in. Now we could replace F with Kx in this formula, and we could get a formula that says energy stored is a half K times X, Kx times X, which is Kx squared. So we could use either versions of that formula for energy stored. What you'll notice is that this actually gives us, we do a half the maximum force times the extension, that actually gives us area under the graph equals energy under a force extension graph. So you may be asked to find that in the exam by adding up or working out the total area, counting boxes and so on and so forth. Now, go across a little bit and generate a bit more space. That only works for something like a spring. If you try and stretch something like an elastic band, the elastic band doesn't actually obey Hooke's law. Well, maybe very slightly at the start. You might get very slight straight, but very soon it will curve off. And it behaves something a bit like that. When you unload it, as you unload it, it remains, for the same force, slightly longer than it was when you stretched it in the first place. So the area under the loading line here is different from the area under the unloading line, force and extension. So the area under the unloading line here, energy released when unloading, and we've got the area under the loading line, which is the blue area I've got there, plus the green area I've got there. So the area under the loading line is equal to the energy used to stretch the elastic band in the first place. Apparently I can't spell stretch. The band in the first place. Which means that the difference between what you put in to stretch it and what is released, which is the blue bit, is the energy wasted as heat. And again, you might be asked to count boxes or squares to find out what that might be. Now, if you have something like a tyre, as the car rolls forward, here's a tyre, the tyre is constantly stretched and then pings back after and then pings back as the tyre rolls forward. So when it's at the bottom next to the road, it's squashed, and then it's de-squashed, for want of a better word, as the tyre rolls forward. Now, doing that, it doesn't release as much energy when it de-squashes as it takes to squash it. So some is lost. So if you can reduce this area reduce wasted energy in compression will increase the efficiency of tyres. If you can make the unloading line as close as possible to the loading line, that area will get smaller and smaller and smaller, and there'll be less energy lost when you squash the tyres as the car rolls forwards, and you'll lose less energy as heat. And that would be quite useful. Now, not all objects return to their original length, like the elastic band does. So this exhibits what we call elastic behaviour. Which means it returns to its original length. Which is over there. Now, not all objects do that. Plot another force extension graph. Now, if you try as our loading line, so we add the weight, stretch it, and now if you unload it, it will form a line parallel to the loading line, for reasons I won't go into. And you'll end up with a permanent extension here. Now, we've talked about the limit of proportionality, which is the point at which they're no longer proportional. The point at which it doesn't go back to its original length, which is after the limit of proportionality, which we'll mark on as E, we call the elastic limit. Because it's the point at which, the point at which it's no longer behaving like an elastic band. It doesn't go back to its original length. So, elastic limit. And these are really, really often confused. Doesn't go back to its original length. Remember, proportional means that they extend in proportion. So the limit of proportionality is the point at which they no longer increase in proportion. They don't obey Hooke's law. An elastic limit is the point it no longer behaves elastically. Think elastic band goes back to the same shape it was when you take the load off. Materials that don't go back to their original length are called plastic materials. So this is plastic behavior. Think of a plastic bag. When you stretch the handles on a plastic bag, they become permanently deformed and don't go back to their original length. So that's everything on energy stored. The next chunk is on stress and strain. So, section 4, stress and strain. So, stress, given the symbol sigma, which is the Greek letter S, lowercase sigma, stress is the force divided by the area. And strain, given the Greek letter epsilon, is the extension divided by the original length. These are important equations, so let's put some boxes around them. So, force is measured in newtons, and A is the cross-sectional and that's quite important. A lot of people miss off the words cross-sectional. Cross-sectional area, not to be confused with the surface area of the wire or whatever it is that you're stretching. And that means that stress is going to have the units of newtons divided by meters squared, newtons per meter squared. Now that is the same as a Pascal, PA. And the formula, you'll notice, is the same as the formula for pressure. So what does it mean? Stress is how much force there is in a unit area. And in this example, our unit area, the unit of area we're using is meters squared. We really need an example to help understand this. So, supposing we had a wire with an area, has an area of 1 meter squared. That is huge. 1 meter by 1 meter, imagine that kind of area. And imagine that massive, huge 1 meter squared cross-sectional cable is supporting 1,000 newtons worth of force. A small car. The stress is 1,000 newtons per square meter. Fine. But if the same weight is supported by half the area, in other words 0.5 meters squared, then the stress now, that is with half the area supporting it, that's the same as 1 meter squared supporting twice the force. So if half a meter squared supports 1,000 newtons, a whole meter squared scaled up would be 2,000 newtons per meter squared. So it gives you an idea about how concentrated, how much force is in this area. The bigger the stress, the more force there is in the same area. And we can compare, to get an idea of how concentrated the force is, we compare for different, we compare for a fixed area, and we say, well, let's make all the areas of all the cables equal to a meter squared. How much force would they then be supporting? And then you can compare. So that's stress. Let's have a look at strain. So we've got extension here. I'm going to run out of space. Extension in meters and original length in meters, and therefore strain is going to have no units because meters divided by meters cancels out. It's just a ratio. So what does it tell us? Strain tells us how much extension we get per meter of original length. And again, we need an example really, e.g. stretching a laboratory string stretching a lab spring, original length about 2 centimeters by 20 centimeters gives a strain of 10, which tells us that the extension is 10 times what the original length is. The total length of the spring, if it's got 20 centimeters of extension and was 2 to start with, is now 22. So that gives us an idea of the kind of strains involved in a laboratory spring, but let's compare that. Imagine stretching, let's say, the cable on a crane, a long cable on a crane, one of those things, precarious looking things that looks like it should fall over, but doesn't. Imagine stretching one of those cables on the crane by 20 centimeters. As a proportion to its original length, that's going to be really, really small. Imagine that the whole thing was 20 meters. If that's 20 meters and we've stretched it by 0.2 of a meter, the strain will be 0.2 divided by 20, which is 0.01. In other words, for every meter of original length, we get 1 centimeter of extension. The cable's being strained a lot less. Imagine that you were put on the rack and tortured by Spanish Inquisition or something like that. If you were experiencing a strain of 10, it would mean that they'd extended you to the extension on you was 10 times your original size. In other words, you were 11 times bigger. That would be staggering. You'd be dead. However, if they stretched you 1 centimeter for every a meter that you were, it wouldn't be very pleasant, but it wouldn't be quite as extreme. Right, with that in mind, I think we better stop and move on to section 5, which is the Young's modulus. So final section then is Young's modulus. And the Young's modulus is defined as stress divided by strain. It's also known as the elastic modulus, given the symbol E. So you might have seen it as either. So Young's modulus is stress over strain, which is force per meter squared divided by extension per meter of original length. Now we can't have divide by divide, and a lot of people really struggle to rearrange that. Easiest way, don't write this down, but the easiest way would be to go strain times Young's modulus is equal to stress, which gives us extension divided by original length times Young's modulus is force divided by area. Bring up the L to the top and take the x down underneath, giving us FL over AX. Or flax, as the way I was taught it at school. Now this looks remarkably similar to the following. Except instead of force divided by extension, we've got force per meter squared divided by extension per meter. So we replaced force with force per meter squared. And we replaced extension with extension So we end up with a formula a value, this Young's modulus value, that doesn't actually depend on area and original length, which looks contradictory because it looks like it does in the equation. But remember that we scale up the force with the area. So if you had, going back to our earlier example, our area of 0.5 meters squared, if we scale that up to a meter squared to work out the force in a meter squared, so we double it, we've also doubled the force. So if we double the area, we double the force passing through that area. And the end result doesn't change. So the force per meter squared is a scaled version. It says if your wire was a meter squared, how much force would be going through it? And the same thing with the strain, it's the extension per meter. So it doesn't matter how long your wire is. If you scale it and go, well, if it was a meter, if we just looked at a meter of it, how much extension would we have got? Well, if you double the original length, you'll get twice the extension, but the strain will stay the same. So this Young's modulus thing doesn't depend on the original length and doesn't depend on the area. L or A. It just depends on the material. So while you couldn't go away and look up the stiffness of copper, you could go away, or the spring constant of copper, you could go away and look up the Young's modulus or the elastic modulus of copper. That doesn't look like a just. I'm going to rewrite that. Just depends on the material. If you plotted a graph of stress against strain, it would basically look exactly the same, and that's going to be measured in pascals or newtons per meter squared. It's going to look exactly the same as our force extension graph. We're going to have our limit of proportionality, and a little bit later on we're going to have our elastic limit, which is the point at which it doesn't go back to its original length. And then, weirdly, you get some other point here called the yield point. And as you stretch a piece of, say, copper wire more and more and more, there's going to get a point where it gets weaker. And this is represented here by the fact that the stress, or the amount of force in a meter squared, decreases slightly, but you're still getting an extension. This is the extension per meter, so the extension per meter original length is increasing, so the total extension must be increasing as well. So from here to here, we've still extended. Each meter of our original length is still extended by that amount. But the force needed to do that has dropped. So the wire weakens temporarily. Now, in order to see this in an experiment, you'd have to unload, you'd have to take off some of the force to see that it was still extending with less force. And you don't do that, so you never see that yield point in any experiments you do. And it's often quite confusing. Next, up here, we've got something called UTS. And that's the largest stress, largest value on the stress axis before the wire breaks. This is the breaking point. And it's called the ultimate, i.e. the largest, tensile, which means under tension as opposed to compressive stress, which would be if you were trying to squash something like a column. Ultimate tensile stress. Largest stress the wire takes before breaking. And you might have come across this with your plastic bag again. So when you start to feel it stretching and stretching and stretching, and it gets longer and longer going this way, the strain is increasing, right? The extension of every meter original length is going up, and you think, oh, it's going to go, it's going to go. So you put your hand underneath to relieve some of the stress, some of the force in those handles, so that you can get to the car quickly. So there are some points on a stress strain graph that you need to be aware of. Now, that is for a Y. You might also see something that does this. And the breaking point comes very, very quickly and suddenly, with very little extension or warning. And we say that that is a brittle material. And it obeys Ohm's law. It obeys Hooke's law up until the point it breaks, pretty much. Now, you might also have a material which goes and becomes really, really long, and that material is ductile. Blue tack is a good example of this. You can draw blue tack out into really, really long extensions, roll it up into little tiny thin bits. So ductile means you can draw it out into wires. So you do need to know what ductile and brittle materials are and what they look like. The other bit that you need to know on the Young's modulus is you had a core practical, which is core practical 4, where you had to find the Young's modulus of a material. So there you will have learned how to read a micrometer and use that to measure the diameter of a wire. And from the diameter, you could work out the cross-sectional area using pi r squared. So you need to be able to read a micrometer scale. And you will also have a much more or potentially more complicated scale called a vernier scale on an instrument called vernier calipers. And you need to know, remember there was 2 scales on there, a fixed one and a moving one, and you had to line them up. So you do need to go back and refresh your memory on how to do those as well. Right, that's it for materials. Thank you for watching.